So now we do the same for the function of y. And so the solution to that now second order ODE, because we have a negative sign, are going to be cosines and sines. So we know that g is going to be equal to a combination of a cosine and a sine. Okay. The thing is, sorry, omega squared, because the constant is omega squared. Yeah. Now, obviously, omega has to do with a angular frequency, but you see here the representation. If your variable here is y, then really you don't want to think about a frequency. A frequency is time. You want to think about a wavelength, right? That's a length scale. So you want to think about a length scale. So instead of writing everything as a function of omega, so I'm going to justify here, y is a length scale, so you want to think about a length scale. And the typical length scale then, which is at this point undetermined, will be the wavelength. And the wavelength is, you may or may not remember, but it's 2 pi divided by lambda. And here lambda is the wavelength. Right? Something like that. Or actually the 2 pi is somewhere else. Let me just, no, this is, sorry. Lambda is equals to 2 pi divided by omega, yeah. Pi f. Is that correct? No? Yes, omega. Huh? Omega here. What is that? This is strange. Yeah. And this, now I'm having a doubt of where the 2 pi is. It is fine. Okay, great. Thank you. Okay, so this is what we have. So think about this omega more as a length scale. So the y distance between, where you have a full period of your cosine. And so now we have an expression for our solution. We can write u, our transient, as a function of t and y. It will look like a constant times an exponential minus mu. And I'll have an omega squared, so it's a 2 pi divided by lambda squared. So let me just put that here. Minus mu 2 pi divided by lambda squared t times a cosine. Well, actually, I'm going to put the constant in there. So a 2 pi divided by lambda y plus b sine divided 2 pi lambda y. And now we use our boundary conditions, right? So we're going to use our boundary conditions. Now, boundary conditions is that the transient velocity is equal to 0 both at y equals 0. I'm going to do this quickly. So at y equals 0, the boundary condition is going to lead to a equals to 0, right? Because the cosine is not equals to 0 at y equals 0. And then we have another boundary condition at y equals d, right? And this is going to impose, well, b cannot be equal to 0. You'll just have the sine term, and therefore you need that the sine of 2 pi y divided by lambda be equal to 0, which imposes that 2 pi times y divided by lambda is equal to pi over 2 plus k, an arbitrary number k times p, pi, right? Is that clear? I need my sine to be equal to 0, and therefore I need that. And so, sorry, this is really bad. The y should be at d, thank you. So you need the sine You need this part when y is equals to d. This pointer is very small. You need this part when y is equal to d to be equal to 0. Right? That part is already 0 because you took a equals to 0. And so that imposes that 2 pi. Sorry, say that again, louder. Oh, you're right, sorry, yes. I was thinking about the cosine. It's k times pi. Yeah? Okay. And so therefore, from there you get that, well, the pi simplify, and you get that lambda is going to be equal to 2d divided by k. Okay, and k can be any number. So actually you can have many of these solutions for all of the values of k. Right? And as k increases, that means what for your wavelength? That it decreases. Right? So k increases means components which are more and more, which are very zigzaggy, which are very have a very high frequency. Okay, so at this point I'm going to stop. Right? I'm not going to go any further than that because it's going to take too much time. So what you have then is you have the transient as a function of t and y, and you found many solutions for all of the different k's. You have potential solutions, right? And so because the equation is linear, you can actually write the solution as a superposition of all of these solutions. So you can write it as the sum from all of the k's of, and now I will have to turn my page, so this is going to be a mess. I'm not going to do that. Times a constant, let me call them ck's, exponentials minus omega squared. So this is where it becomes tricky because I need to go back to my notes here. So I'm going to have a minus mu and 2 pi divided by lambda is going to be k divided by d. So let me help me out. K divided by d squared. Okay, so minus mu k divided by d squared times t, right? And I have sine of k d will be the same. I have to go back there because I don't remember. It's 2 pi divided by lambda, so it is k divided by d. Okay, that's fine. K divided by d, 1. Okay, so you can write your solution as that. And I may have done a mistake here. There might be 2 pi's missing or stuff like that. I think there are mistakes in there. So I invite you to do the math a bit more carefully than what I just did. The whole thing is that now you just need to identify, the point is the solution is going to look like that, plus or minus some constant which are floating, which I encourage you to really derive in details. If you found what the errors is, that's great. The important thing here is to see that you will identify those constants by going at the initial condition. Right? So when t equals to 0, you have this sum of ck's, exponentials are all zeros, times sines of ky divided by d. Right? And here you just need to essentially take the Fourier series of your initial condition to identify the ck's. You may have seen that before. So this I don't want to discuss. I'm going to do here a Fourier series of initial condition, right? I would not ask you to do something like that in an exam. Fourier series is not really the point of IFT. Just know how you would get there. If you are facing a problem like that one day, just
in the power of the exponent.
Yeah.
Within the square of
the p. There's a pi. Yeah. There might be a pi somewhere. Let me just at this point I just don't want to think about this because it has the right scalings. Right, it has the right dimensions, and this is what I want to discuss. Okay, so I'll just go over the math and I'll just post the solution where the math is correct. What is important here is to note that, so once you decompose in Fourier series, of course you have different, your initial condition has different frequencies in that. You've seen that sort of, you can Fourier decompose like this flat signal. It has higher frequency parts and it has lower frequency part. The important thing is that when you look at this solution, there are two things. This term here tells you roughly how high is the frequency of this component, and you see that when the frequency, when your wavelength is short, right? That means when k is large, when the wavelength is short, d over k is large, right? Then what happens to the time constant? It becomes really short. You can think of that. You can think about this guy. This here is t, is an exponential minus t divided by d squared divided by mu, right? This is where, hold on, times k squared. Is that correct? No, the k is on the other side. Okay, so this is like this, d divided by k squared, yeah. Right, so here you have your characteristic time scale, which we discussed before. So this is your initial condition, you have a sign, and you see here that this sign is going to go to 0 because you have an exponential minus t divided by a certain time scale. Note that your time scale for the decay of the transient is, you have it here, it has a d squared divided by mu. This is what we discussed. You see it? This is becoming messy, so I'll clean up the notes, but you have a minus t divided by, if you want, a characteristic time scale for that particular wavelength to disappear. That t tau k, that characteristic time scale, which corresponds to how long it will take for the transient to get to 0, that is the typical diffusive length scale we've discussed. Is that clear? And you see that it scales with d squared divided by mu. You have the d squared divided by mu. Right? But you have something else in that, and that is the fact that you have this 1 over k squared, which tells you that this is going to happen much quicker for short wavelength. When the wavelength is short, right, the short wavelengths will be diffused much quicker, because viscosity is going to, if you have a very small gradient, right, in velocity, then viscosity, the diffusion will act smaller. Diffusion acts, you have two things to think about, the diffusivity, but also the gradients. The sharper the gradients, the faster the diffusion. It's the same with temperature. The sharper the temperature gradient, the faster it's going to get initially flattened out. Okay, so this is what you have here. Okay, I'm not going to go any further in that. I'll just clean up the notes, and then I encourage you to just go back to the notes once they're cleaner and once you can just follow the derivation. There's another derivation which I will not do, and it's a similar one, and it's a startup for an unbounded flow. I'll put that one into your homework because we can't do it in class. Into your next homework, and I'll just briefly describe the problem. It's very similar. Let's think about the startup of a quet flow. We had flow inside of a gap, and now we'll just have flow, but there's just one plate, and the other one is infinite in that side. So we have at t equals 0, we start with a 0 profile, and at t equals 0 plus, we'll start the lower plate, and now it starts to move at u. Okay, so what we'll have velocity like this, right, which slowly will diffuse into the bulk. Right, so you see the analogy with quet flow. Yeah. Now there will be one major difference. Can anyone already see what the difference is going to be? Yes. Yeah, it doesn't. Why? Yeah. Maybe the applied mathematicians would already have an idea about. It translates into a mathematical problem, right? Do you see it? Yes. Why? Because there's no length scale. Right? You see a problem here. If you have an unbounded flow and you have an infinite plate, you have no length scale. So that's your first hint that somewhere along the line, when you're trying to solve, you use a similarity solution. Okay, so in the end, it's a problem which looks very similar to the other one in a quet flow, but in a quet flow you have a length scale, you have the gap size. Here you no longer have any length scale, so the way you will change your PD into an ODE is going to go through by trying to find a similarity solution. Okay? And it turns out it works out for this problem. They're all mathematically, they're all very related. Huh? So this problem you'll have in your homework. Okay, and we're going to leave unidirectional flows and move to lubrication theory. Okay, so new topic. This is lubrication theory. And that is another case where, this is in Kundu chapter 9.3. So we're still discussing laminar viscous flows. So our first discussion of really viscous flows had to do with unidirectional flows, right? Because the flow was unidirectional, even though the Reynolds number might not be completely zero. You don't have effect of inertia, and you only have the viscous term left. And there's another case, we'll discuss another application where the inertial term drops out, and you only have the viscous term left. And that also has to do with the geometry of the flow, and this is when you have a thin film. So, lubrication. What is the lubrication geometry? An example. So you have seen lubrication flows before. The first example is if you have a wall and you paint your wall. You have a very thin film. Right? I mean, this is actually, of course, for you, this is just it might be just of relevance for every so often when you paint your wall, but industrially, this is a very generic process of coating. And so in any coating application, so this is paint. Paint on the wall. This is a lubrication film, so a thin film of fluid. A very thin. You have two very different length scale: a length scale across the film and a length scale along the film, and those two are very different. What happens usually when you paint? What is annoying when you paint? Droplets, right? So if we have time, you'll find that if you just take lubrication, and if you just take lubrication, you'll find that naturally you cannot avoid the formation of droplets of, I know how you call it in Dutch, but of those little things that you then always have to flatten out many times, and it's just an instability in the problem, which you cannot avoid. So if we have time, we'll discuss that. Another example, also thin film, is spin coating. Right, so if you need to coat, in microfluidics, for instance, if you want to coat with PDMS a certain surface, or if you want to create silicon wafers, you drop fluid, viscous fluid. Now you do it in industrial processes as well. Right? You drop fluid and you dump it onto a spinning plate, right? And then the fluid is just going to be ejected towards the end, like that. And maybe it's not very well drawn, but this is spin coating. In spin coating, again, the flow will fall within lubrication theory, because you will have a long length scale and a very short length scale. Yeah. So this is example 2. If you think about geophysical flows, the flow of lava. Now I'll change color. I'll do red for lava. So this is not lubrication, but when the lava just flows like this, that will be lubrication. Okay. Again, you have a very different. You have two very different length scale. So this is also lubrication. Now there are certain cases. Let me tell you directly. there are certain cases where the two length scales are very different, and it's not lubrication. So a river is not a lubrication problem, and you know that because if you're thinking about the flow of water in a river, the effects of inertia are very important. Those are the ones that dominate. So there will be at some point a non-dimensional numbers that will tell you whether or not you have a lubrication film. So it's not just the geometry. Of course, the viscosity of the fluid will also come in. And in the case of lava, because lava is very, very viscous, this is why you will have a lubrication. And then air bearings, let me just continue because I need to speed up a little bit. So lubrication theory, applies to thin films. Anytime you have a thin film, this is when you have lubrication. Sorry, you have lubrication oftentimes when you have a thin film, but really what will define lubrication is if because of this thin film, the effect of inertia can be neglected as opposed to the effect of viscosity. So it will be just in the lubrication layer. Essentially, what characterizes the lubrication layer is that the important effect is the effect of viscosity. It's a viscosity-driven flow. So it's when you have a thin film geometry and effect of inertia. Is negligible compared to the effect of viscosity. Now, usually this is always what is characteristic of the Reynolds number, and you'll see that for lubrication theory it will also look like a Reynolds number, right? But it will be the Reynolds number times the ratio of length scale. So there is a Reynolds number in there, but it's not just the direct Reynolds number. So you have to be a bit careful about how you characterize, how you determine whether or not you are in the lubrication regime. So now number 2, we'll simplify the Navier-Stokes equation in the lubrication limit. So here the motion is going to be very similar to what we did before for boundary layers and then for unit dimensional flows and now for lubrication. We'll look at the equations, we'll look at our assumptions, and we'll come up with a criteria in terms of non-dimensional number for when our assumptions are valid. And we'll discuss, I will discuss here lubrication flows in a 2D planar geometry. And you could do lubrication in axis. Essentially, in IFD, everything will always be either 2D planar and axis symmetric, which is the same essentially. Right? And in that case, I'm going to derive everything in 2D planar, but you should be able to do the same simplification in axis symmetric when you have flow, say, in the Z and R direction, and nothing changes with the theta direction. So here in class, I'll do 2D planar. And so here is our typical geometry. We have a plate and we have a flow, a layer of fluid. We're going to call capital H the typical length scale across the flow, and we'll call capital L the typical length scale in the direction of the flow. And here I have an interface, right? Think of this as a layer of paint. You have your interface, and now I'm going to use back the notation which we introduced, I noted down, on Tuesday or Thursday 21st of September. So this is now almost 3 months ago. And the height of the interface is going to be h, and here it's only a function of x and time. Yeah. So you'll see certain things that we saw in September come back now. Now we also need scales for velocity, and at this point, just like in the case of the boundary layer, now we have it. Of course, you have flow. Most of the flow will be in the u direction. So we'll call capital U the flow in the u direction, but we don't know what the scale is for the flow in the v direction. Okay, so and at this point it's unknown, so we'll still keep it as a capital V. And now we have to non-dimensionalize our equations. So we need to pick characteristic length scale for everything. Now x will be non-dimensionalized with L. That makes sense. Y is going to be non-dimensionalized with H. And U is going to be non-dimensionalized with capital U. And V is going to be non-dimensionalized with capital V. And what are we going to do with pressure? This is the fourth time we do that now. Huh? At this point, you just want to leave it open. Right? You don't know exactly what it's going to scale with. It will scale with the largest term. Yeah? So at this point, I'm just going to be pressure scaling with pressure. So P, I'm going to call pi 0 the scale for pressure. P0, sorry, not pi. P0 is the scale for pressure. And how are we going to scale time? Knowing that the flow now happens, it's a lubrication flow, so most of the flow happens in this direction. If flow happened in this direction, then it will not stay a lubrication layer for a long time. So most of the flow happens in this direction. So what would be the natural length scale, like time scale for T? Huh? Yeah, U of L. It will be, yes, L over U. L over U is going to be our characteristic time scale. Very good. And with that, we non-dimensionalize. Now I only have 15 minutes left, and I want to get a bit further than I am. So, so I will just start the motion, and I know you've seen that many times, so by now I know that you're confident that given the quietness of your own study room, you'll be able to do that. The first thing you want to do is to non-dimensionalize. Well, non-dimensionalize is to look at the continuity equation. From your experience, what will the continuity equation give us? Just like in boundary layers, it will give us the scale for the v direction. Yeah. So we have that. So the first term here scales with u divided by L. The second term will scale with v divided by h. Right. If you were to conserve mass, those two terms should be on the same order of magnitude. Right? Otherwise, they can't cancel each other. So that gives you a scale for v. So you find that u divided by L will have to scale with v divided by h, and therefore v will have to scale with h times u divided by L. Right? And our first, let me just go back to here. Our first assumption, if you have a lubrication layer, is of course that h is much smaller than L. That's the number one assumption. We have a thin film. So you see directly here that V is going to be much smaller than U. Yeah? So I mean, if this is troubling you, then it shouldn't. Just think about mass conservation. Right? You have a flat interface. Right? Think about a velocity. Think about mass conservation. A typical velocity in the v direction. Right? If I have flow in the v direction over length scale L, if you have mass conservation, then that means that all of the mass needs to exit here. And so you need to have U, so your volumetric flow rate here will be V times L. And that will have to exit here through, and it will be U times H. Right? That's another way of seeing why the two have to scale together. Yeah? it's mass conservation. So you can also think about control volumes or the integral scale to get a feel for why those quantities have to scale like this. So this is the continuity equation, and now the X momentum equation. So I have rho partial u over partial t plus u partial u over partial x plus v partial u over partial y is equal to minus the gradient, sorry, not minus the gradient, minus partial p over partial x plus mu times the second partial of u with respect to x and plus the second partial of u with respect to y. Okay, so I'm going to just quickly write the scale of all of these terms. So this term here scales with rho capital U divided by our time scale, which was L divided by U. So it's L U squared. This term scales with rho, so it scales with rho U times U, so U squared divided by L. So it also scales with rho U squared divided by L. And this term scales with rho. I have V, so V is H divided by L times U. U squared divided by H. So it's also U squared divided by L. Okay? I'm just going to simplify those H, and I'm left with U squared divided by L. This will scale with P0 divided by L. Now we're going to see something, some of the same things again. From those two terms, which one is going to drop out? Huh? The one with respect to x or y? X, yeah, because x is a long length scale. So this is the one you're gonna have very little gradient in the x direction for you, but a lot of them in the y direction. So here, this term scales with mu u divided by L squared, and this one scales with mu u divided by h squared, but h is really small. So you directly know that this one is going to be small compared to that, and this is because h is much more than L. Yeah? Now if h is much more than L, then what do we have left? We have left these terms here, which all scale with rho u squared divided by L, and we have this term here, which is mu u divided by h squared. So the fundamental assumption of lubrication, so the lubrication limit is when we can neglect the effect of inertia, and therefore when rho u squared divided by L is much smaller than mu u divided by h squared. Okay, so this is going to give you something, a condition which looks like a Reynolds number. It's going to be rho u times h squared divided by mu L. So another way of writing that is I will write here. Yeah. So it's the Reynolds number. Let me write that. I can write it as rho u h divided by mu. That will be the Reynolds number based on the length scale, which is across the flow, times h divided by L. Okay. And this number here needs to be much more than 1. So the lubrication assumption you can rewrite as Reynolds number. I'm going to put an h here to make sure we don't confuse our. You could define a Reynolds number based on the long length scale. Here we define a smaller number based on the smaller length scale, right? But just this Reynolds number smaller than 1 is not enough, right? This number times h divided by L is going to be much more than 1. Right? And this factor H divided by L is one of the reasons why, even if the viscosity is not very large, and even when all the dimensions seems very small, sometimes you're still in the lubrication layer. So you may have heard of air bearings, right? If you wrote, you have a thin layer of air, and in that thin layer of air, you have a lubrication approximation. We'll see that lubrication approximation, for these air bearings will translate to very high pressure, right? And you're still, even though you have air, and the velocities are quite high, so you would think the Reynolds number is large, and if you computed the Reynolds number based on the longer length scale, it will be large. Even if you computed the Reynolds number based on H, the gap length, it might not be too small, but you have on top of that this factor H over L, which is really small, right? So the lubrication approximation in some case, is valid, even though you might think, well, it's air and it's moving relatively quickly. Okay. So that's the condition. This is the lubrication limit. Okay. And now pressure, right, will adapt to the highest term. Pressure will scale with the most important term. So now you can deduce a scaling for the pressure. So this is the lubrication limit. Now what is the scaling for the pressure? And this is where you'll see that the pressures can become really high for lubrication. So P0 divided by L will scale with mu U divided by H squared. So your scale for pressure is mu U L divided by H squared. So you note that your characteristic scale for pressure already has a 1 over H squared in the denominator, right? And H is small, so P could be, doesn't have to, but P could be very large. Yeah? There will be some lubrication flows which will be driven by, which will not be driven by pressure. So think, for instance, the wall, the paint which you just leave on the wall. What do you think the pressure is going to be in the film? Atmospheric pressure, exactly. Yeah, you have an interface. The interface is relatively flat, so when you imply a boundary condition, you know that the pressure in the fluid is going to be the atmospheric pressure, and then across, then you have very small distances to the wall, and you have no flow in that direction, so you don't expect much pressure changes. So actually, the pressure inside of the fluid is mostly just atmospheric pressure. Right? But in other cases, you'll see that if pressure does develop in a lubrication layer due to some pushing down, due to flow also in the V direction, then it can become quite large, the pressure. That's the whole basis for air bearings. Now I have 5 more minutes to do the Y component. So this is the X component of the momentum equation. Let's do the Y component of the momentum equation. So what is left of the Y component? Now, if you do draw again an analogy with boundary layers, because again, we were looking at a similar geometry. You should have an idea already of what will come out, and you'll see it's going to be somewhat similar. Hold on. There could be a body force in there, right? There could be a body force in there. Of course, if there is no pressure and the flow is driven by the body force, then you cannot neglect the body force. So this term here, you always have to think very, especially in lubrication layers, you have to think: is the body force relevant or is it not relevant? And the big clue as whether or not it's relevant or not usually is it driving the flow or is it not driving the flow? Right? So just think, for instance, about yeah, I don't know what to think about. But just don't always cross it. You know, you have to think about different problems, and in some cases, the whole point is that the flow is like lava, for instance, right? Lava is driven by what? Gravity. Yeah. If you now cross it out because you're like, no, I just want pressure. Yeah, then you have a problem. Yeah. So you know, you always have to. In those cases, sometimes the body force is going to be important. So let me just leave it here there. Okay, now I have rho partial v over partial t plus u partial v over partial x plus v partial v over partial y equals minus delta p delta y plus mu second partial of v with respect to x plus second partial of v with respect to y plus potentially the body force in the y direction. Now we have the same. This term is of course going to be smaller than that one, right? And now when we write all the scales, we can do that. It's a bit tedious. So rho, here I have rho, v scaled with u divided by u times h divided by l. So I have h divided by l times u, and t is l divided by u. So I have a rho u squared h divided by l squared. This is that term. This term here will be the same, rho h u squared divided by l squared. This term here will be rho u squared h squared divided by l squared divided by h, so it's going to be the same. Am I correct? Yes. So all of these terms scale with rho h u squared divided by l squared. Now I do have a typical scale for my pressure. You know, the pressure might be relevant or not, but I do have a scale for it. So this term here now will scale with potentially mu u l divided by h to the cube. Right, so this is already giving it away. This is going to be huge. It can be huge because you have a 1 over h cube. So this is going to be essentially the term which dominates. And this term here is mu times u divided by l divided by h cube. So you have a 1, so then you're left with 1 over h LH. U L times H. So you have a 1 over H, so it's also a big term, but it's not that big. Now this term here, because of the lubrication approximation, this term here is going to be much smaller than these two. That should be, you just do it, you'll find out that this term is really small. So those terms are all going to be neglected compared to those. And when you compare this one and that one, right, you see that this term is going to be small compared to that one. Yeah? So the only term you're left with is the pressure term and potentially the body term in the lubrication equation. And with that, I finished the derivation for the lubrication, the governing equation for lubrication. So this is 0 equals minus partial p over partial y plus potentially the forces in the y direction. So let me just summarize. So you have the continuity equation, and then you can reproduce the momentum equation here and the x momentum equation here. So 0 equals to minus partial p over partial x plus mu second partial of u with respect to y squared plus f of x, and 0 minus p minus y plus the body force.